So last time we left off, we had looked at doing our particle concentration check for magnetic particle inspection. Remember, we need to have the machine running. Before we perform a magnetic particle inspection, we need to have the pump on the machine running to get those particles in suspension for about 15 minutes or so, 15, 20 minutes before we take a sample. And then when we take a sample, we take a 100 milliliter sample, we let it sit for at least an hour, and then we can read the concentration of particles within that sample. So here it's showing 0.3 milliliters of particles. Normal range is 0.2 to 0.4. And so groups have started this on Tuesday, and I think our machine right now, the bench is sitting at 0.25. I'll probably bring it up a little bit here now that we got people starting to use it again. So just kind of pay attention to that as we go. Looking at the actual process and the magnetization of the parts, magnetic particle inspection can be done using alternating current or direct current. Now, our bench that we have only does alternating current, and that's the majority of magnetic particle inspections are going to be that way. The reason for that is we have alternating current coming into our buildings, and so it's just stepping that current up in order to create that electromagnetic, that magnetizing force. And so if you have a DC is a more specialized process, and the equipment is more specialized where it has to have transformers and rectifiers to turn that AC power that we get in a building to DC. And so the equipment tends to be more expensive and bulky, but it also is more specialized, so you don't see it as much. The advantages of using DC is you can get a deeper magnetism penetration. So magnetism on a part primarily forms close to the surface. And so if we're looking for subsurface defects, we can, in some cases, use DC to find subsurface defects. They won't, it's not a crack that makes its way to the surface, but rather there's a discontinuity down below the surface, and that's still going to cause some disruption in that magnetic field that is at the surface of the part. And so we have to get that deeper magnetic field penetration in order to see those. So again, when I say not all equipment is capable of DC, most equipment, in fact, is not. Portable equipment is almost always AC, because all it is taking, it plugs in, it's just a big electromagnet horseshoe-looking thing or a couple prods, right? And then AC is the easiest to do. DC, you need a fixed bench that's got some transformer rectifier equipment in. So here is a diagram of kind of field strength in relation to distance from the center of the part. So this is DC magnetism. So you can see at the very center of a part, you actually don't get magnetism because the fields on each side cancel out, right? They're going essentially opposite directions here. If you think about the magnetic fields going around, the outside of the part, if we run current longitudinally, we have circular fields, right? Over here, we'll say if it's going clockwise, if our flux lines are going clockwise, on the top here, the flux line would be pointing to the right, and the flux line at the bottom would be pointing to the left. Equal magnitude, equal distance, they're going to cancel out when we get to the center. So you can see the magnetism is basically zero at the center. It peaks at the surface, it's strongest at the surface. And then we can sense, we take our Gauss gauge, right, and we move it around the part to sense that magnetic field. What we're sensing is everything to the right of that peak here, okay? And you can see as you go one radius out, the field strength gets cut in half. If we go 2 radii out, it's a third of what it was originally, right? So it drops logarithmically as we move away from the part. For a DC surface, we're working with AC, and AC looks more like this. So you can see there isn't nearly as strong of a magnetic field inside the part right here, right? The majority, the strength of the field is by far strongest at the surface of the part. And then it drops away quite rapidly outside the part, but you still have a magnetic field, a presence of a magnetic field that you can detect once you get outside the radius of the part. This is especially true when we have those circular fields. Those of you that have started it, you notice you probably have to put the Gauss gauge really close to the part to get an indication. And that's because that field drops off. So if I put them side by side, they look something like this, where you can see the effect AC on the left, DC getting that deeper penetration, stronger internal magnetic field on the right. And you can see it does for the same magnetizing force, same radius part, it is going to have a stronger, magnetic field that is stronger, magnetic flux field that's stronger outside the part as well. But again, for surface cracks, AC is, gives us a plenty strong magnetic field that we're able to find surface cracks. And the majority of things we're going to be looking for in aviation are going to be more of a surface crack situation. Really, the area you see internal magnetization taking place is more in a production environment, where it's something like if you're doing castings or forgings and you want to make sure there aren't voids inside the part caused by either an air bubble or caused by, in forging, you can get the metal folding over on itself. It's called a lap. And then you end up, it comes back on itself, the metal squeezes together, so it's closed off, but then you got an opening inside. My kids are really into slime right now. They take their slime, they fold it over, and then they squeeze it to make farting noises. My 7-year-old thinks it's awesome, right? Or shoving it into the jar, right? Yeah. Is anyone familiar with Peachy Babies? Oh, God. Okay. YouTube marketing at its finest. It's a company that makes slime. And they have all these YouTube videos reviewing slimes and making slimes. And their slimes are $16 for a little jar that big, and then shipping on top of that. So it's like $25 to buy a jar of slime. Yeah. Welcome to Christmas at the Lindenbergs. Demagnetizing. So after we've done our inspection, we want to make sure that our part doesn't maintain magnetic field. I mentioned it earlier on, right? The two big issues there in aviation are parts that are magnetic on an aircraft can disrupt the communications and navigation equipment, right? Because a lot of navigation equipment is trying to sense the magnetic flux field that's around the Earth, especially if you have a what's called an AHARS system, attitude heading reference system, which is purely flux-based. Even if you have what's called an IRS, inertial reference system, they often still have flux gates, flux measurement thing to get an initial position. And then they use inertia in order to calculate ongoing position, whereas an AHARS system calculates position by constantly monitoring the magnetic field. But that's one. The other part is, like, especially if you're talking about an inside of an engine, if you have a part that's magnetic and you get any kind of ferromagnetic material that's wearing, that wear material, that metal dust and metal particles, rather than suspending in the oil and working their way to the filter and being filtered out, they stick to whatever parts are magnetic, and then it increases the wear on those parts. And so we want to make sure that we demagnetize our part. So the way we demagnetize is we have to use AC for this, and a part is placed in the magnetic field produced by an AC coil. So we're not going to run current through the part now. We're purely going to use the coil running current around the outside that's creating a magnetic field area. And the magnetic field is slowly reduced in magnitude. Okay? There's two ways to do that. The one, I'm going to start with the second one here. Magnetic field is slowly decayed from around the part. That is, the current running through the coil is slowly brought down to zero. Okay? The other way to do it is, and this is a lot faster and I think easier, and this is what I'm going to have you do, is rather than decreasing the current going through the coil, you also can decrease the magnetic field the part's experiencing by physically moving it away from that magnetic field. So we're going to hold our part in the coil, we're going to hit the button on the machine to run current through the coil, and then we're going to draw the part away. And we're going to do that a couple times. You change the orientation, draw it away, change the orientation, draw it away. And that collapsing field that it experiences, that field that's dropping in magnitude, is going to bring the part back to a demagnetized state. Now, the way that works goes back to this diagram. Now, we saw the top left corner here, right, earlier in the lecture. This is that magnetic flux, the diagram showing, our part. Now, if we start with a magnetized part, we're going to start on this outermost loop, right? So as the magnetizing force is high, we're going to reach our saturation point, right, at each end. Right? This is with an AC coil here. Now, what's happening is as we reduce that magnetizing force, right, this is the amount of magnetism the part has is B, right, the y-axis. So as we reduce the magnetic force, you can see, we're starting here, right? This was our magnetized part. It had retained magnetism. Here's the retentivity point. So it's going to get pulled negative, and then it's going to get pulled positive. Now, the next time it comes around, because the magnetizing force is less, it's not going to fully saturate. It's going to end up at this dashed line, this second dashed line from the bottom here. And then it's going to go up to this one here. And then it's going to work its way in, and you can see it's going to get further and further from reaching the saturation point each time until we effectively get to a magnetizing force of 0, till the part's moved far enough away from the coil, or our current running through the coil has dropped to 0. And so that is what is going to bring our part back to this demagnetized state. And especially if we're like changing the orientation of the part as we do this. So if I have a coil here, if I bring my part out this way, and then I turn my, then I turn my part and turn it this way, maybe flip it upside down and backwards, right? If I'm turning it and changing the direction each time, this is also going to be changing the direction it magnetizes the individual atoms in there, the field. So it's going to scramble all those individual magnetic fields that are with each atom that makes up the part. And once they're all sufficiently scrambled, the part itself is no longer magnetized. And we can use a Gauss gauge to verify that. If we start moving our Gauss gauge around our part, we won't get any deflection of the needle because there is no magnetic flux field that's going to cause that needle to deflect. And so we can say our part's been effectively demagnetized there. Okay. Here's the current curve. This is just showing the AC current getting weaker, and then the field getting weaker till it's 0. They kind of took this curve and split it out into two curves here. So that's how we can use that flux density curve to kind of see what's happening when we demagnetize our part. And then the final step, not here, but we probably don't want to leave our carrier solution and whatever particles are left on our part. So we're going to go take our part and we're going to do a post-cleaning on it. We're going to remove that. Now, one of the things we will do, even though the part's demagnetized, it doesn't mean there aren't still particles that are stuck to it because of surface roughness and friction and things like that, and it's wet with the carrier solution. Surface tension is going to hold those particles on there. So as we do this over time, we're done with our part. We take it and clean it. When we go wash it in the washroom or clean it off, the particles that are there are going to get washed off into our wash tanks. So over time, our bench is going to experience something called draw out, and that is where that particle concentration is going to drop over time because we're washing particles off in the cleaning room rather than putting them back into the tank. And so that's why we're going to have to add particles to the tank every so often. So even though it's not magnetized, there'll still be a few stuck to it. Okay, that wraps up magnetic particles, magnetic particle inspection.